Right now, somewhere near the edge of a black hole, there is a moment frozen in time, a particle, a photon, maybe something more complex, suspended at the boundary between the universe we know and something we can barely describe. From our perspective, it has been there since before humans existed. From its perspective, no time has passed at all. It is not dead, it is not alive. It exists in a place where those categories don't apply, because death requires time, and time in our universe is not the same everywhere. It runs fast in some places, it crawls in others. It stops completely at the edges of the most extreme objects in existence. And once you understand that, once you really feel what that means, your entire picture of what is permanent and what is temporary in this universe shifts underneath your feet. I want to start with a question that seems simple and turns out not to be. What is death? Not philosophically, not spiritually, physically. What is death, described in the language of physics? Death is a process. It is the irreversible breakdown of organized structure. A living body is an extraordinarily complex arrangement of matter, running on energy, maintaining its own organization against the constant tendency of things to become more disordered. Your cells repair themselves. Your immune system fights entropy. Your metabolism constantly converts energy to keep the whole structure running. When that stops, when the energy input ends, and the repair process is shut down, disorder wins. The organization breaks down. The complex structure becomes a simpler one. That is death. In the language of physics, it is entropy increasing. It is the second law of thermodynamics taking over. It is complexity collapsing into simplicity. And here is the key thing. That process, that increase of entropy, that collapse of organization, requires time to happen. Entropy increases over time. Disorder spreads over time. Death unfolds over time. Which means that where time slows, death slows. Where time stops, death stops. And time does not run the same everywhere. That is not a hypothesis. That is one of the most thoroughly tested facts in all of physics. Let me explain why. In 1905, Einstein published his special theory of relativity. It made a prediction that sounded impossible. It said that a clock moving through space runs slower than a clock standing still. Not appears to run slower, not seem slower from a certain perspective, actually runs slower. The moving clock accumulates less time. Less time passes for it. It falls behind. This is called time dilation, and it is real. We have measured it directly. In 1971, physicists placed atomic clocks on airplanes and flew them around the world. When the planes landed, the airborne clocks were slightly behind the clocks that had stayed on the ground. The difference was tiny, nanoseconds, but it was exactly what Einstein's equations predicted. The moving clocks had genuinely experienced less time. Today, every GPS satellite in orbit has to account for time dilation or it would give wrong positions. The satellites are moving fast relative to the ground, which makes their clocks run slightly slow due to velocity. They're also higher up in Earth's gravitational field, which makes their clocks run slightly fast. We'll get to that in a moment. The net correction is applied in real time every second, or navigation errors would accumulate to kilometers per day. Time dilation is not a theoretical curiosity. It is an engineering requirement built into the technology you use to navigate. So the first form of time dilation is velocity. The faster you move through space, the slower you move through time. These two are traded against each other. Speed through space and speed through time add up to a constant, the speed of light. When you move faster through space, you move slower through time. A photon, moving at the maximum speed through space, moves at zero speed through time. Light does not experience time at all. The second form of time dilation is gravitational. This comes from Einstein's general theory of relativity, published in 1915. It says that time runs slower in stronger gravitational fields. Closer to a massive object, time ticks more slowly. Farther away, time ticks faster. This too has been directly measured. Atomic clocks at the top of tall buildings tick slightly faster than clocks at the base. The difference is minuscule, 1 part in a quadrillion per meter of height difference on Earth, but it is measurable, and it matches Einstein's prediction exactly. Clocks on GPS satellites, sitting higher in Earth's gravitational field than ground-based clocks, gain about 45 microseconds per day due to gravitational time dilation. Engineers subtract this correction before the velocity correction is added back. Both effects are real, both matter. Now let's follow these two effects to their extremes, because that is where the title of this conversation becomes physically literal. A black hole is a region of space-time where gravity is so extreme that nothing, not matter, not light, not information of any kind can escape. At the center is a singularity. Surrounding it is the event horizon, the boundary of no return. Cross the event horizon, and you cannot come back. But here is what happens to time near a black hole's event horizon. As you approach the event horizon, gravitational time dilation becomes extreme. For an outside observer watching you fall in, your clock appears to slow down. You appear to move more slowly. Your signals arrive more and more stretched out, more and more redshifted, more and more delayed. As you reach the event horizon, from the outside observer's point of view, you appear to freeze, to stop moving entirely, to be suspended at the boundary forever. From their perspective, you never actually cross the event horizon. You hover there forever, not moving forward, not aging, not changing, frozen at the edge of time. From your own perspective, falling freely toward the black hole. You cross the event horizon without drama. You feel nothing special at that boundary. You continue falling. Time passes normally for you. You have your own experiences, but the universe outside has moved on without you. An infinite amount of time passes outside while you fall through a finite experience of your own. I want to sit with this for a moment, because it is genuinely extraordinary. An outside observer sees you frozen at the edge of a black hole. From their perspective, you have been there for the entire history of the universe after the moment you approached. You have not aged. You have not died. The physical process of death, the entropic breakdown of biological structure, has not happened from their point of view. Your biological processes, stretched by infinite time dilation, have slowed to a complete halt. This is not poetry. This is what the mathematics of general relativity describes. Death, as a physical process, does not happen for an observer at the event horizon as seen from outside. Time dilation has reduced the rate of every physical process, including the processes of decay and death, to zero. Now, practically speaking, other things would kill you well before you reach the event horizon of any black hole we know of. The tidal forces, the difference in gravitational pull between your head and your feet, would stretch you apart long before you reach the boundary. Physicists call this spaghettification. It is not a comfortable fate. But for a sufficiently large black hole, a supermassive one, millions or billions of times the mass of our sun, the tidal forces at the event horizon are actually quite gentle. You could cross it without being torn apart. You would simply be in a region from which there is no return, and you would, from the perspective of the universe outside, be frozen there forever, a moment stretched into eternity by the geometry of space-time. Let me now step away from black holes and talk about the velocity side of time dilation, because this one is, in principle, more relevant to anything that might actually travel through the universe. Imagine a traveler moving at 99.9% of the speed of light. At that speed, time dilation is dramatic. For every year that passes aboard the ship, roughly 22 years pass outside. The traveler ages 1 year while the universe ages 22. At 99.99% of light speed, the ratio jumps to about 70 to 1. 1 year aboard, 70 years outside. At 99.999% of light speed, it becomes roughly 700 to 1. The closer you get to the speed of light, the more extreme the ratio becomes. Time dilation grows without limit as you approach the cosmic speed limit. A traveler, moving at an arbitrarily close fraction of the speed of light, could, in principle, cross the entire observable universe within a single human lifetime of their own experienced time, while billions of years passed outside. Now think about what this means for death. A living thing, a biological organism, ages according to its own internal clock. Its cells divide on a schedule tied to its experienced time. Its telomeres shorten at a rate set by its own biology. Its brain processes information according to time as it experiences it. If the traveler's time is dilated, if a year of their experience corresponds to 1,000 years of outside time, then their biological aging slows by the same factor. Their cells divide 1,000 times more slowly relative to outside time. Their telomeres shorten 1,000 times more slowly. Every physical process that drives biological decay and death occurs 1,000 times more slowly relative to the outside universe. Death still happens. Eventually, the traveler still ages, still decays, still dies in their own experienced time. But relative to the universe outside, they age and die at a fraction of the normal rate. The universe can grow old and transform while the traveler barely changes. This is time dilation as a form of extreme longevity, not immortality, not a stoppage of death, but a radical stretching of how long a physical process takes relative to the external universe. Now let me talk about something deeper, because I've been discussing biological death, the end of living organisms. But physics has a broader concept of death, the death of stars, the death of galaxies, the heat death of the universe. And time dilation plays a role in all of them, though in different ways. Stars die when they exhaust their fuel. The sun, for instance, has been burning hydrogen for about 4.6 billion years and has about 5 billion years left. When it exhausts its hydrogen, it will expand into a red giant, shed its outer layers, and collapse into a white dwarf, a dense, slowly cooling remnant that will take trillions of years to fade to darkness. That timeline, the life and death of a star, is measured in the time of the universe's own clock. But for anything experiencing strong time dilation near a black hole or moving at near light speeds, that entire stellar life cycle could pass in what feels like moments. A traveler circling close to a stellar mass black hole at just above the event horizon could experience 1 hour while thousands of years pass outside. They could watch a nearby star evolve and die in what feels to them like an afternoon. The deaths happening in the universe around a time-dilated observer are not happening at the rate that observer experiences. The universe ages around them while they barely age themselves. Death, for other objects and other beings, unfolds at a rate completely decoupled from the observer's own experienced time. This is the truth the title points to. Death doesn't happen everywhere on the same schedule. The rate at which physical things end, stars, organisms, structures, depends on where you are relative to gravity and how fast you're moving through space. The universe does not have one universal clock. It has as many clocks as there are physical systems in it, each running at its own rate, set by local conditions. Now I want to bring this to something even more fundamental, the arrow of time. Why does time go forward? Why do we remember the past but not the future? Why does entropy increase? Why does disorder spread rather than spontaneously reversing? This is one of the deepest questions in physics, and the answer connects directly to what death is. The laws of physics at the fundamental level are almost entirely time-symmetric. The equations that govern how particles interact look the same, whether time runs forward or backward. Collisions between particles, quantum interactions, electromagnetic processes, play them in reverse, and they still obey the same laws. And yet, time clearly has a direction. Eggs break but don't unbreak. Ice melts but doesn't unmelt. People age but don't unage. Why? The answer is entropy. The second law of thermodynamics says that in any closed system, entropy disorder tends to increase over time, not because the fundamental laws demand it, but because there are vastly more ways for a system to be disordered than ordered. A broken egg has far more possible disordered states than unbroken ones. The odds of random processes producing a broken egg assembling itself back together are so astronomically small as to be effectively zero. The arrow of time, the direction from past to future, is statistical. It is the direction in which entropy almost certainly increases. It is the direction in which complex ordered structures break down. And death is one of the most dramatic examples of this. Life is a local temporary decrease in entropy, a region of organized complexity that maintains itself by consuming energy and expelling disorder. Death is the end of that temporary pocket of order. The organism becomes part of the general increase of entropy. Its complexity disperses. Now near a black hole, something interesting happens to entropy. The black hole itself has entropy, enormous entropy, proportional to the area of its event horizon. As things fall into a black hole, the total entropy of the system, the black hole plus its surroundings, still increases. The second law is not violated. But the rate at which entropy increases, for an observer near the event horizon, is stretched by time dilation. The entropic processes, the processes that drive decay and death, slow down as seen from outside. The arrow of time still points the same way, but its pace is different. Death still happens, but it doesn't happen on the same schedule everywhere. I want to bring this back to something personal because I think the physics here connects to something that many people find both troubling and fascinating about the nature of existence. We live our lives inside a particular flow of time. Our biology runs at a particular rate. We age at a particular pace. The world around us changes at a familiar speed. This gives us our sense of time as something fixed, universal, steady. But the physics says this is a local experience. The rate of your clock, the pace of your aging, the speed of your processes, the timeline of your death is set by where you are and how fast you're moving. Change those parameters dramatically enough, and you change the relationship between your experience time and the time of the universe around you. This is not comfort exactly, You still die in your own experienced time, at whatever rate your biology determines. But it is a fundamental truth about the nature of time and existence that most people never learn clearly. That time is not a universal river flowing at the same rate everywhere. It is a local phenomenon set by local conditions, running at a rate that depends on mass and motion. And death, which is a process unfolding through time, inherits all of that variability. In some places, the processes that lead to death are stretched. In others, they are compressed. At the extreme edge of a black hole, they are from outside frozen. The universe does not have one clock. It has trillions upon trillions of clocks, each set to a slightly different rate by its local conditions. And the biological clocks inside every living thing, the clocks that tick off the time toward death, run within that same variable framework. Death doesn't happen everywhere at the same pace. It never did. We just lived our entire lives in a small, comfortable corner of the universe where the differences are too small to notice without atomic clocks and GPS corrections. Step outside that corner, toward extreme gravity, toward the speed of light, and the differences become impossible to ignore. The frozen moment near the black hole is real. The slowed aging of the fast-moving traveler is real. The variability of time across the universe is real. And death, being a physical process unfolding through time, is real in the same variable, local, physics-dependent way. The universe does not deal in universals very often. When it does, they are remarkable. The speed of light is universal. The laws of physics are universal. But time is local. And everything that happens through time, including the ending of things, is local too. That is the truth hidden in the physics. And it is stranger and more beautiful than the certainty we were born believing.